Yeah, let me double check. Yeah, I think we're good. Okay, so this is lecture 3, the basics of linear regression. Just to kind of where we are. So this is the 6 topics in general. Hopefully we can cover. The last 2, we're going to just roughly talk about it. The first 4 are the focus of the course, because this is just a 1 semester course. Honestly, graphical model and reinforcement learning, each one of them itself, really worth for a full semester of class. So regression. So again, hopefully you still remember the differences among these different contents. Regression is about why it's a continuous target variable. Classification about why it's a discrete symbolic variable. Unsupervised model means there's no y. So in general, when there's no y. And learning theorem is really about properties of f, and also, so it's mostly about properties of f. And we're going to talk about it later. Bias variance trade-off is the main focus we're going to cover here. And graphical models, it's about the dependencies among the features, among how you describe all your samples, the dependencies. It's more like a conditional dependency from a probabilistic sense. And reinforcement learning is really it's quite different from the supervised, unsupervised, or all of those. I mean, you can think about this as more like a wrapper task. So all these previous tasks, more like a prediction task. 1 sample, I'm trying to predict something. And by reinforcement learning models a trajectory. It's really trying to model how your learned program interact with the environment. So in reinforcement learning, you can use supervised learning. You can use unsupervised learning. You can use semi-supervised learning. So it's not like reinforcement learning is not on the it's not a direct comparison counterpart to supervised or unsupervised learning. It's more like a wrapper setting. So like I emphasized many times, I want to use this nutshell mental representation to structure all of the algorithms we're going to learn. So this is the first algorithm. So let me try to use this for the first time. So for regression and the task is to predict toward a real value. So in this case, we just target only 1-dimensional y. So our task is a continuous variable task. So in terms of the data form, more concretely on the data level, it's really just that last column in your data, they are real numbers. And just to kind of review what we learned before, I mean, we call the rows as data. We represent the rows. We use rows to represent data, sample, instances, records. They're all meaning the same thing. And we use columns to all the columns except the last column to represent features, variables. I think they're also called regressors, independent variables, or covariates. They all mean the same thing. Feature variables we use to represent our instances. And the last column, in our case, there's only 1 target variable. Just the last column, we call them target, response, label, dependent variable. They're all meaning the same thing. It's just the one we're going to predict. Predict to what? And that's the target variable, and in the regression case, this is a continuous variable. So again, these train and test 2 phases, and in the training phases, you're going to learn the model. In the testing phases, you're going to apply the model on the data points, and then trying to see how this data, how the model, how the program I just learned behave on the future data. Future data is really using test data to simulate those data you haven't seen in the training data. So again, so train, test, 2 phases. Now we're going to more concretely, what you truly in your programs when you do this writing is the training data, test data, and it looks like each row will be represented as this is a row vector because we are our default. So the default vector is column vector, so that's why it has the transpose because default is a column vector, so it has to be transposed into a row because here I'm representing the row of my current matrix. And why I'm going to emphasize this, you're going to understand why I'm trying to talk about loss function formulation in just a few slides forward. This is the Y train and Y train given label, Y train one test given label. So this is our data in the mathematical notation form. Okay, so we'll talk about task. Now let's talk about representation. So in summary, the representation of linear regression is just fx, or my predicted y, is just a weighted linear summation of x features. So that's my representation. What do I mean a linear representation or a linear summation of x? So let's just use this really simple example to show geometrically and visually. So this is a function, fx equals wx plus b. And if you plot it in geometrically, and let's use x just as x-axis and y as y-axis, the points built up from x and corresponding to fx will be just a line. That's what we mean a linear model, a linear regression model, because the relationship just represented as a linear line in the 1D case. So hopefully as you remember, the b parameter is representing when x equals 0, what's my y number, my values. And the slope, that w represent one x, make one change, how much y changes. If w equals to 2, it means when x changes one interval, y changes 2 intervals. W is slope, b is intercept. It represents how y is when x equal to 0. Very, very elementary, but in the end, this is it. So let's just do a very simple example. So this task, this formulation is, you already know the f, right? But our task is, we are given training data and we don't know the f. We do not know f, we need to look for f, right? So the given formulation normally is so there are a lot of exam questions or quiz question like this. So you're given the training data, behaves 1, 2, and 3. So this is 2, 3, and 4. And I'm given 3 points. And that's my training data. My training data is, there are totally 3 points. 1, 2, 2, 2, 2, 3, 3, 2, 4. So this is my training data. I'm trying to figure out the best line to predict, to map the x to the y. And this is actually super easy. You can just eyeball, right? Just eyeball the best line can predict all the 3 points very nicely. So, and then I'm just, my fx, so this is the training data. My fx is equals to wx plus b. And now let's use the first x. The first x with first f1. What is f1 here? f1 equals to elementary, right? What is f1 now? W plus b. What is f2 now? Yeah, elementary school, right? 2w plus b. And f3, what is f3 now? 3w plus b. Now what? How can I know w and b then? How can I know w and b? Yeah. So I have to figure out an error function, right? And there are many kinds of error function, right? I mean, I have to represent it as an equation. And let's just see this, let's call that loss function. Loss function is with the parameter w and b, right? The only unknown now is w and b. And I want to measure how this f1 close to y, right? Because that's my goal. So what I really need to write there is w plus b. Let's use a quadratic function. And this is representing the first point error. Question about this? Oh, yeah, sorry, it's -2. Yeah. And then you just do another point plus 2w plus b minus 3 quadratic plus 3w plus b minus 4 quadratic. And you try to minimize this loss function by minimize it. And that gives you the best w and b fit your data. So w and b equals to argmin. We normally write this like argmin. Yeah, it's a little crowded. Equals to argmin loss function, which w and b are the only unknowns here. And I hope you know how to optimize this function. How to optimize this function? Yeah. So there are certain properties of this function because this is a quadratic of its parameter. So I'm going to do that later, but just to let you know, you can actually tell, I hope there's a blue color. So assuming I learn so this is a perfect case because you can get a perfect line, feed the 3 points. But there are a lot of situations you can't, there's no way. So there may be the fourth point here, the fifth point here, and there are points like this, maybe here. This W plus B or WX plus B minus Y is exactly what geometrically? So this is my given Y, labeled Y. But if I'm using this line, what Y do I get? It's really these X positions, Y numbers, right? It's D here. And that W plus B or WX plus B minus Y is this area. How far is my Y to the Y on the line? And it's accumulated quadratically across all the points. So that's it. So this is actually a linear regression. And by minimizing this loss function, that's how you find the best W and B. But how to minimize this, right? Even though someone talk about it, gradient equal to 0, we need to, I'm going to derive it in just a few slides. Question about this, and this is almost everything about this lecture, but on a concrete example. On a concrete, very easy example. Please do ask questions, because if you can't understand this, no way to understand more abstract version in the matrix form. And this is the most fundamental.
Why do we need square?
Good question. So you actually can use others, right? It can be absolute differences, right? So first of all, it's a loss function, right? You want to measure it if it's truly off, it's a positive number. The more off, the bigger the number, because of loss. So quadratic is a good function to guarantee it's non-negative. And at the same time, the reason why we do quadratic function at the beginning, because we do have other type of functions in other algorithms, is quadratic function is the easiest to solve. So that's why we pick this, because it's super easy to solve the quadratic loss function. So that's why we do this as the first, because you can derive it very easily. But whenever there's other type of absolute functions, and it's very hard to derive, and also hard to guarantee some terminology I'm going to throw you, which might be a little bit like magic. This is a convex function. This guarantees the convex properties of the loss function, but I don't want to talk too much for now. Okay, so this simple illustrated example clear? Has to be absolutely clear. If this is not clear, every pages later will be hard. Sure.
My question is, how can we prove that when we use the square loss, we can find an optimal solution?
That's about convex properties of this loss function, and I will talk about it briefly in the few slides coming. Okay. All right, so based on the questions, it looks like you understand much deeper than this page, because this is elementary, but it's fundamental. I always find simple, so no matter how complicated mathematical it really is, there should be an intuitive example to show almost the whole part of the intuition. And I feel this is a good question, good illustrated example to show the intuition. Okay, so again, I just repeat this, and we're going to do this later to show here. So we showed the 1D case, right? 1D case is really just x try to map to y. So let's just do a little bit more concretely. We always use this silly example is, so how to predict the rent price based on properties of the renting house. It's the living area, of course, it should be proportional, like positively increased. The bigger the house, the more the rent, right? Hopefully this is a linear relationship. And of course, there's also other factors like maybe locations, and that makes your x not just one-dimensional representation. It's not just points in this one-dimensional x. Now you have two-dimensional, x1 and x2, and then you're trying to learn a linear function from x combination to the y. So this is the one you learn. So it's not a line anymore, it's a plane. Okay, so when your input is two-dimensional, what you truly learned is a plane. One is when your input is three-dimensional, what you learn is a hyperplane. It's on the higher dimensional, it's a hyperplane. And the linear line and the plane is just its simple specific forms in the one-dimensional and two-dimensional case. You might find confusing to kind of confuse with what we covered in the classification, right? If you remember in the classification, the last class we talked about, and there are two-dimensional feature representation, but you learn a line to separate the two classes, right? So I'm going to review this in the classification stage. But just remember, in the classification, what you actually learn is a stair function. This may be a little bit, you might not get it, but it's going to be very clear when we reach the classification phase. So in the classification, that example, we plotted, visualized, there's no y we visualize. We only visualized y through colors. But in fact, you actually can visualize the y as the third into a three-dimensional space. What you truly learn in classification is a stair function is, so the red part is one plane, and then there's a big drop, and then the blue part is a -1 plane. So that's a stair function. Just to, if you're confused, don't worry, we're going to reflect on that. But if you're curious, that's the differences of this figure versus the other figure. The whole point is, because in this y, your y is continuous. This is a regression task, right? Your y is continuous. But in classification case, your y is symbolic. You project it into 1 and -1 in that problem, in that formulation. All right? Okay, so so mathematically, it's really just represented as, so we have wx plus b. Let's put the notations in a more concise and coherent manner. So we represent the intercept as theta 0, the first as theta 1 for the first feature. For the second feature, we represent it as the theta 2. You can go on into theta p plus xp. And this is the representation. Y prediction equals to theta 0 plus theta 1x, theta 2x2 onto theta p xp. But we like to make it concise. So rather than writing this as this form, we want to write as this form. So we want to represent it as a vector-vector multiplication operation rather than a lot of scalar operation and a big summation function. Okay, let's see why this equals to this. So it's really just an inner product operation. I hope you still remember about what is inner product operation. Inner product operation is, I think I have a review slide. It's just sum of product or elements in similar positions for two vectors. So you can write them as more two, this triangle parenthesis, or you can write as a form, one x vector transposition times the y, or y vector transposition times the x. The equivalent equals to each other. The reason is, so this is very important. This is almost the trick we always use. Inner product is order invariant. The reason is, this is a p, assuming this is a p times 1 vector, p times 1, p times 1. After inner product, what you get is 1 times 1. And because it's really this operation, the inner product is really just x transposition y or y transposition x. It's a scalar, right? It doesn't matter who is first. And it's the element summation, product summation. Okay, let's come back to see our linear regression formulation. So this is element product formulation, right? Theta 1, x1, theta 2, x2 until theta p, xp. And the only difference is this is theta 0. And I just do an arbitrary, I actually just assume there's a 1 here. And then this is exactly x, the new x is 1, x1, x2 until xp. And then I can write my fx function as x transpose theta or theta transpose x. Question about this? There are actually a lot of questions can be asked, and this is a fundamental move. Yeah, maybe just not to get you confused, maybe this is better. Go here. Okay, I'm converting a element product summation operation into a vector operation. There's a fundamental reason why we do so. The reason is, if you perform this through the library NumPy, or actually the NumPy uses the underlying library called BLAS. This operation is a lot faster compared to if you do for loop I from 1 to p, perform this multiplication then plus theta 0. This is faster. This makes use of a lot of CPU parallelization, vectorization trick in the underlying library. And we want to represent them as much as we can to use of the BLAS library because they are good, they are faster and efficient. And the vector-wise is even actually pretty trivial. When you go to matrix form, it's even more dramatic. It's actually a lot more dramatic. You want to convert those kind of for loop operations. You can write as for loop into matrix vector product operation or matrix operation. Because there's a lot of architecture level speeding up library tricks. People already wrapped up under. And this is not a good practice. And this is good practice. It's because of the computer, how the computer works. All right, Questions? Okay, so we represent that you really just applied a function on a sample, right, into a vector form. Okay, so now we know the representation. We finished the third check mark from our nutshell. Now let's go to the scoring function. So now we know how to represent the f, but we don't know how to learn theta. It's very similar to our simple examples. We know representation, but we don't know W and B. In there, we actually speculate square loss functions are good. And yes, they're good. So this is how you write out the square loss function, right? But this is bad representation because you have to do for loop, for each possible examples in your training data, minus the true y, and then take a square and then do the summation. And this is not an efficient way to write it out through programs, right? And you want to convert it. So the loss function we're going to use is called sum of squared error. And our goal is to pick out the optimal theta to minimize this function, which we already showed in here. It's fx plus y take quadratic over all the training y. And verily, on the 1D case, it's really this differences. Y, this is my given y, this is my predicted y. And in the 2D case is this is given y, this is the predicted y. So keep that in mind. And what I should write here, it should be quadratic. Yeah. So what we use in the loss function is this y minus y hat take a quadratic as one of the contribution of this sample to the whole loss function. So yeah, that gives you this, right? It's a summation over all the training data. It's predicted fxi minus the yi, take a quadratic, and then summation. Like I just mentioned, this is not good. I mean, it's slow. We want to convert it. I think I have a page maybe. Yeah. So I want to convert it into something like this. This equivalent to x theta minus the y true, and it's all into the matrix or vector form. It's a little bit tricky how I get from here to here, but actually we're using the same trick we just used. So the first is I want to show you is how do I get x theta? How do I put the whole training matrix into this form? So the first is how do I represent if I apply the fx on the whole training data? And this is how you get it. So I think there's a little, sorry, we can make it too low. Yeah, maybe this is better. Okay, yeah, this is better. Okay, so again, I want to put representation into matrix or vector forms. The first vector form can be just, okay, so if I apply for fx on x1, what I get is x1 transpose theta, right? We already derived this. If I apply the fx on x2, this gives me x2 transpose theta. You just put all of them as rows. And this is the predicted y vector. You just apply the fx function, and this is how you get the predicted y1, predicted y2, the predicted yn. And this can be concisely represented as this, which is the whole data matrix representation times the theta vector. So I think I have a page about this. It's really because x equivalent to this representation, and if you apply theta, if you do x theta, it equivalent to, because you remember what's matrix vector multiplication, right? Matrix vector multiplication is each row of the matrix times that vector. If you times theta here, times theta here, it's exactly x1 transpose theta into xn transpose theta. And the x theta is this concise representation we like, because this operation is quick. We do a parallel, it's actually parallel implemented inside the class, because all these operations here they are not coupled. Okay, I use a lot of terminologies. I hope you understand it. They are parallelized. They use parallel implementation to do that n multiplication operation. It's fast. In GPU, this is even faster because you have even more parallel processors to perform this. Okay, and this is your representation of y hat, right? And then that's, you convert the summation operation into yeah, I think I need to do this decomposition. Okay, we have a page about this. Yeah, so let's still do this. So now we know we can do this whole x theta into that form, right? But our loss function is this representation. Okay, so this representation, if you look at it, it's a element-wise product and then take a summation. This is exactly a vector inner product operation. And the vector is x theta minus y. And let me rewrite x theta minus y as the vector here. Is xi transpose theta minus yi. So let me do so this is 1 x2 transpose theta minus y2 onto xp, actually xn in this case. Xn transpose theta minus yn. And this is the vector. This vector's inner product is, so this is the vector. This vector, if we calculate the size, so we already did x theta, right? We know x theta is n times p times 1, and this gives me n times 1 predicted y hat. And then you minus a n times 1. This together gives you n times 1 vector. This is just to confirm. This is a vector. And this vector's inner product is this summation form. And that's exactly the second step. Again, I'm using the trick. Summation of summation of element-wise product equivalent to the inner product. It's in this case just a little bit special is, it's actually this page, disorganized. So the trick I used is A transpose A equals to summation AI quadratic, I from 1 to n. And here A is that A vector is x theta minus y. Question about this? It's just a trick, but it's very efficient and we need this. Let's go back to this page. I'm going to reorganize this. So you actually converted this for loop representation into the matrix representation. And then you can just do, hopefully you remember how to do transposition inside x theta minus y. And then you know how to do multiplication of the first with the transposition already added there, and then just do a multiplication. And that gives you this form. This is your loss function formula. And now we're going to optimize it. So this is your concise notation of loss function. Question about this? We all just use this trick. Sure.
What did you divide it by 2?
Good question. You're going to see it why, because when we take gradient, the quadratic form will give a 2, and then it cancel out that 2. But actually, I don't need to have that 2. It's just to give the gradient a clean form. To make the gradient a clean form. Okay, so now you understand this notation of loss function. So I think you already know this. We finished 1 through 3, and now we go to the 4th item in a nutshell. How do you optimize it? So you already have the loss function form. How do you optimize it? There are many different ways to optimize it today because this is such a great, simple loss function. We can directly just solve it through linear algebra, and that gives you this thing. There's just a special name. Don't worry. It's really just we can solve it. It's called normal equation based solution. You can also use gradient descent and stochastic gradient descent to solve it. Okay, so this is our form, right? And you already know why. So A transpose A, and that A is a concise matrix vector product operation. So how do you minimize it? You just take gradient, you set it to 0. That's it. Why? So for this one, if you take its gradient, it's very easy to get its gradient. So I normally do this whole derivation on board, but yeah, so I think you should be able to do it by yourself, right? Okay, so let's just do this. It's already here, right? J theta. How do I take gradient of J theta versus theta? I just take the gradient versus each element, right? So first is the first term. Theta transpose x theta. You take its gradient is equivalent to x transpose x theta. You actually just can't memorize it, but this is one of the homework. You need to derive it. And that's the first term, give you, so we still have 1/2 to x transpose x theta. It's from the first term. Then from the second term, you should just get it. The second term, if I do versus theta, what is its gradient? Minus x transpose y, right? Yeah, actually the same thing. Yeah. And then the second term, what is its gradient? Look at the second term and third term. They are actually inner product of the same thing. The second term will also give you what at the third term. The third term will also give you, it's the y transpose. This term is actually equivalent to theta transpose x transpose y. Because again, the same trick. It doesn't matter who is x, who is before, who is later, it's an inner product. Remember, right? This pen is killing me. Okay. So remember, what is x theta? We just derived x theta is n times 1 vector, y predicted, right? N times 1. And what is y? That's the true y. Y bar is the true y. True y bar transposition is 1 times n, right? And look at this term. It's totally the same. It's just inner product with different form. And this also contributes. The third term also contributes x transpose y in the gradient. Then the last term. The last term in terms of gradient, what is it? That y transposition y. Take gradient versus theta. What is it? 0. Okay, and then this equal to 0. What do you get? 2 got canceled out, right? That's exactly x transposition x theta equivalent to x transpose y. I should have a white bar here. Yeah. And this is called a normal equation. And then you just solve it. So how do you solve this? It's a linear function. X transposition x theta equals to x transposition y bar. We can just do what? You put the x transposition y to the right, right? That's how you solve it. And this is our solution. I think there might be a little bit, a few hiccups in some of the derivation here. Try to read the slides more carefully, but keep in mind the reason why we converted this, the for loop formulation into matrix formulation is to make it fast, to make use of the underlying matrix vector libraries. And if you're still confused, I can actually add a simple, so this is just trying to tell you that derivation and then the gradient of this, why the second gradient, theta transpose x transpose y, take gradient where theta give you x transpose y, And this is the simplest example. Very easy. And then you can read the extra slides to get to know the quadratic form. How do you take gradient? So these to use partial derivatives and gradient. Hopefully you still remember from your math class. And you just need to review. There's this differences of derivatives, partial derivatives, and gradient vector. And we actually ask you to review those. And this is the whole derivation about how do you convert J theta into the form, into this decomposition form, which you just need to do a step derivation by yourself. It should be pretty doable at your current level. So and also I have the gradient of each that element, and then how do you derive this whole thing together? And then I want to see something a little bit extra. So when you have this gradient, set it to 0, the operation itself actually has assumptions. The assumption is X transpose X can be inverted. And hopefully you still remember, not all the matrices can be inverted, and there are certain properties actually the matrix need to satisfy to be invertible. And also the form, we know, the theta is X transpose X. I always do this exercise just to, more like a practice. So let's see, this X transpose X is a P times N matrix times N times P matrix. And the resulting matrix is a P times P matrix. And the inversion, in the end, is a matrix of P times P. So the reason why I'm doing so is, if the form of X transpose X, the form of X transpose X is, this matrix is positive semi-definite, and it's if X is full rank, it's guaranteed the X transpose X can be inverted. So it's just guaranteed by the form itself. If X is full rank, X transpose X can be inverted. Here, full rank is N larger than P. It's actually the minimal requirement. P is smaller than N. When P is larger than N, so hopefully you still remember the multiplication is, so when P smaller than, actually larger than N, because this matrix is P times P, right? Two matrix product, the rank of the product will be smaller than each. And if N is smaller than P, and it's guaranteed this matrix rank is smaller than P. And for P times P matrix, if its rank is smaller than P, no way it can be inverted. So this is the simplest trick you know. When you have more features than samples, you actually cannot do this because it's not invertible. So this actually tells you there are certain conditions you can't use this solution to solve a linear regression, even though this is such a simple formulation and a simple solution formulation. when you have more features than samples, this is not durable. You can't do this solution. Questions? I skipped the basic review of linear algebra. I guess maybe some of you are confused by because all these are covered in the basic linear algebra slides. So what's the rank of a matrix? What's the rank properties of a matrix product? And you can all get it from the slides in the lecture 2, and that it's much clearer explained there. So this is actually totally extra, and for those of you who want to learn it, just read this. A convex function have a single point at which its derivatives goes to 0. And this point is guaranteed to be a minimal point. Intuitively, one-dimensional function is convex if a function's second derivative is positive everywhere in that range. Intuitively, if a matrix multivariate Hessian is positive semi-definite, this function is convex, which is the case of our case, because so this is our derivative, right? Our derivative is x transpose x theta minus x transpose y. Let's see the second derivative of the Hessian. Let me do so what is it? This is actually the second order derivative, right? What I should write is, would be better is this. So I'm really just taking gradient of the gradient. If I'm taking gradient versus theta, this has nothing contributed. The Hessian is x transpose x. So my function's Hessian is a grand matrix form, and this is positive semi-definite if x is full rank, which connected to the next page, it's guaranteed. It's guaranteed my loss function is convex. It has the minimal points. It's questions about this? This is a little extra, but I hope some of you can be useful. Like, this can be useful to help you understand it deeper. So again, this loss function is good. Its function can be easily solved. At the same time, it also has good properties. It's convex because the Hessian, the form of the Hessian, or the form of the second order gradient, second order derivative. I'm abusing terms in a few cases. Okay, so all right. So too many of this, yeah. So again, to summarize, the J theta is that quadratic form, its Hessian is x transpose x, and it has the grand matrix form. It's guaranteed to be positive semi-definite if x is full rank. So that's why J theta is convex, and it's guaranteed if you're taking gradient equal to 0, that point is the minimal point. It's the best point to minimize my J theta function. And this is the logic behind why do you just take a gradient set to 0, that gives you the best minimal point of J theta. All right, so we have all this closed form solution now. So yeah, I actually have a few slides about the ranks. I mean, feel free to read it if you're not very clear. Just how the multiplication, the rank, is the minimum of each. So I already mentioned, right? There are situations you can't use this. When the number of points n is smaller than the p. It's totally just n smaller than p, it's guaranteed that inversion doesn't work. So for those situations, you actually have to add something. And this is the next topic we're going to cover. So how do you do it if you have maybe more features than samples? How do you make it work, make that inversion work? And there's a lot of trick, especially the regularization trick is for this purpose. And now the last point is what I try to emphasize again and again. So why do you convert all those theta 0 plus theta 1, x1 plus theta 2, x2, this kind of for loop possible implementation into vector times vector, because you want to make use of the BLAST library, right? And then more concretely, let's see, what's the computational cost of this normal equation derived solution? Let's just do, assuming like we don't know the library tricks speed up the operations. What's the, I already write there, but I want you to think about it. What's the time cost of x transpose x? This is a matrix times matrix operation. And each matrix is n times p. It's a p times n times p matrix, right? So just think of a naive operation. N vector, it's the first vector is size n times this row vector times the column vector. It's an n vector times an n vector. What's the time cost? Actually, it's an inner product operation. Q. It's yeah. Let me write it here. It's that specific xi transposition x. Maybe let me write xj. So this is a 1 times n times 1. So what is this time cost? Element-wide product and the summation. Summation is constant. That's we always, right? Assuming that's a constant operation. Element-wide product operation is how many of element-wise product operation here? N. Okay, let's just write O in there. So each one of this row times column is On. And how many of this row versus column product? Think about it. How many? I make it wrong. Is it P times N or N times P? It's 1 times N times N times 1. So, like, this is On, this is correct. And then you have 1 times, so you have the first row times all the other columns. How many of those operations? P. And then you have the second row times all the columns, another P. Now how many of these rows you do this P operations? Actually OP quadratic. Yeah, it's OP quadratic. So you have this P quadratic, this type of operation, and that's why you get OP quadratic N. Yeah, so this is just a naive, most naive way to think about it. And then you think the inversion may be a little bit trickier. Let's just keep in mind this cubic cost. And you can actually do, I mean, the whole cost is ONP quadratic plus P cubic, right? When N larger than P, when N larger than P, who is dominating in this term? when n larger than p, who is dominating in that term is the np quadratic term, right? So matrix multiplication is dominating here when n is really large. But in truth, and this is not the true cost because I have a lot of those, of course you can do naive for loop, and there's a lot of algorithms in numerical operations and do much faster. For example, this called strengthened algorithm make the this is actually 2 n times n matrix. We just have n times p, right? So if we change one of ours in our p into the n, is n cubic is the same thing, and they have much faster into 2.8. They're even faster to 2.3. So libraries, when you have big N or big P, make a huge difference in cost. There's also memory cost. I don't even put it here, and hopefully, there's not just the CPU seamed. Hopefully, you know what is seamed. Multi-threading. There's also memory hierarchy structure you can make use to speed this up. But all those are wrapped under the BLAST library. And